The Wheatstone bridge is an electrical circuit shaped like a rhombus. ABCD. The four sides of the rhombus are made up of four different resistors. R1 to R4. Across the vertical diagonal BD of the rhombus, a galvanometer is connected to detect current. Across the horizontal diagonal AC, a cell is connected. I1 to I4 are the currents through the corresponding resistors R1 to R4. IG is the current passing through the galvanometer. Let G be the resistance of the galvanometer. The formulae we derived for series and parallel combinations of resistors and cells are not sufficient to determine all the currents and potential differences in such circuits. Let us now apply Kirchhoff's junction rule at junction points B and D. At point B, I2 minus IG minus I4 is equal to 0. Let this be equation 1. At point D, I1 plus IG minus I3 is equal to 0. Let this be equation 2. Let us now apply Kirchhoff's loop rule to the two closed loops, ADBA and CBDC. Loop ADBA. Across points A and D, by applying the rule, we get minus I1 R1 plus IGG plus I2 R2 is equal to 0. On simplifying, we get I1 R1 is equal to I2 R2 plus IGG. Let this be equation 3. Loop CBDC. Across points B and C, by applying the rule, we get I4 R4 minus IGG minus I3 R3 is equal to 0. On simplifying, we get I4 R4 is equal to I3 R3 plus IGG. Let this be equation 4. As a special case, the values of R1 to R4 are chosen in such a way that IG becomes 0. Now, substituting IG equal to 0 in equation 1 and simplifying, we get equation 5. Substituting IG equal to 0 in equation 2 and simplifying, we get equation 6. Substituting IG equal to 0 in equation 3 and simplifying, we get equation 7. Substituting IG equal to 0 in equation 4 and simplifying, we get equation 8. Substituting for I3 and I4 from equations 5 and 6 in equation 8, we get I1 divided by I2 is equal to R4 divided by R3. Let this be equation 9. From equations 7 and 9, we can write R2 divided by R1 is equal to R4 divided by R3. Let this be equation 10. Equation 10 denotes the relationship between the four resistors for the galvanometer to produce zero or null deflection. This relation is therefore called the balance condition. The application of this balance condition is a practical method to determine an unknown resistance. Let us assume that R4 is the unknown resistance. R1 and R2 are known resistances. We gradually change the value of R3 till the galvanometer shows null deflection. The bridge now is in balanced condition, and we can apply equation 10. Rearranging the terms in equation 10, we can write R4 is equal to R2 into R3 by R1. Let this be equation 11. Equation 11 is used in a practical circuit, which is called the meter bridge. The schematic diagram of a meter bridge is as shown. A meter bridge consists of a 1 meter long standard resistance wire of uniform cross-section held taut between two ends of a metallic strip bent at right angles at the ends, placed alongside a meter scale. There are two gaps, one on the left and the other on the right. In the horizontal part of the metallic strip where two resistors, one of which is known and the other unknown, are attached. The end points A and C, where the wire is clamped to the metallic strip, are connected to the cell. One end of the galvanometer is connected to the midpoint B of the metallic strip between the two gaps in it. The other end of the galvanometer is connected to a jockey, which is a metallic rod with one end shaped like a knife edge. The knife edge end of the jockey slides over the wire to make electrical contact. R is the unknown resistance of a given resistor which we have to determine, and the resistor is connected across the right gap in the metallic strip. A standard resistance, S, in the form of a resistance box, is connected across the left gap in the metallic strip. The knife edge end of the jockey is moved along the wire until the galvanometer shows a null reading. Let D be the position of the jockey on the wire when the null reading is obtained. Let R be the resistance per centimeter of the standard wire. As the area of cross-section of the standard wire is constant, its resistance is proportional to its length. Thus, the resistance of the AD part of the wire is equal to R into L. And the resistance of the DC part of the wire is equal to R into 100 minus L. The Wheatstone bridge and meter bridge circuits are very similar. The table shown gives the comparison of resistances between the Wheatstone bridge and the meter bridge. As the current in the galvanometer of the meter bridge is 0, the circuit in the meter bridge is a balanced one, and hence we can apply equation 11 to the circuit. Substituting the expressions for the resistances in the meter bridge in equation 11 and simplifying, we get the expression for the unknown resistance R is equal to S into 100 minus L divided by L. Thus, we find the resistance of an unknown resistor using the principle of the Wheatstone bridge in a meter bridge circuit.